Hi again, everyone. Welcome to renegotiating the boundary between database latency and consistency. Let me introduce myself, Zach Leviatan. I'm VP Product at ScyllaDB. Before that, I spent some time as a product manager at Oracle, and even before that, as a product manager mostly in the telecom domain. And even before that, I was a developer, but that many years ago, probably before some of you were born. And I will let my other co-host and the main speaker for today, Kostya, to introduce himself.
Thank you, sir. Yeah, I just checked myself for the earliest book on databases I have. It's like from 80s. So I've also been involved in databases for a very long time. But let's get back to the slides.
Thanks, Kostya. And Kostya will be take my place and present the main part of this presentation shortly. So you have to see my face for some time, but don't worry. So what is ScyllaDB? ScyllaDB is a NoSQL database designed from scratch to achieve three goals. The first is high availability, the second is high throughput, and the last is low latency. And this was the main goal that we set for ourselves. The latency part, actually, we don't going to talk about in this session, and I'm talking about the latency of each node independently. We'll cover latency of the distributed aspect of the database, but a lot of the work in the database in Scylla was actually invested in algorithm and mechanism like shard per core and storage and things like that, which are critical for latency, but not going to be the focus of this session. You can consume or use ScyllaDB in three main fashions. The first one is open source. Go to github/ScyllaDB. Scylla, you can see the code, download it, compile it, or download it as a Docker, open issue, even send patches if you want to contribute. The second variant is the Scylla Enterprise. It's a closed source product, which is very similar to open source. Everything we're going to talk about today, and 95% of the code or so is the same between open source and enterprise. Enterprise do include a few special features, some around performance, some around security, etc. And the last but not least is Scylla Cloud. Scylla Cloud is what is now called database as a service. It's basically Scylla Enterprise, but managed by us. So if you go to a Scylla Cloud web application, you can launch a cluster on AWS, GCP, and we will manage the database for you. Other than that, it's the exact same database used for open source and enterprise. Some of our customers, and we have many more customers, even more open source users. You can see they come from a lot of categories, a lot of domains. But I think what is common between all of the use cases that they are typically handling of large, big data, as it's called. So we're talking about starting from 1 terabyte to many terabyte. And they all need low latency and high throughput. So Scylla Sweet Spot is the online request when you either build an application or dashboard or edtech or bidding or anything like that, and you are looking for a sub-millisecond response time from your database. ScyllaDB is probably a good choice for you. So what are we going to cover today? So I already introduced ScyllaDB. Next, I'm going to spend some time talking about NoSQL and the trade-off between consistency and availability today or in the past as well in NoSQL. Then I'm going to switch to Kostya to deep dive into the problem statement of the session, trade-off between consistency and latency in ScyllaDB, in particular for metadata. Spoiler alert, is going to use the Raft consensus algorithm for that, and going to explain what is Raft, how we're using it. And last, we're going to explain a little bit about the next step and hopefully have some time for Q&A as well. So what is NoSQL and why it was introduced? So databases, of course, as Kostya mentioned, are with us for many, many years, decades. And it started, or not started, but at some point it's looked like rational database is all that you need. You have SQL, you have transaction, and you can run all the database on one server, and life is good. But at some point this model break, and it break when the internet was introduced and we come to learn a term like web scale. And practically it means that not all the data or all the throughput can fit into one server, and you have to switch from one server or a small cluster to a distributed model. And by distribute, I mean in the data center and actually across different data centers. And this is where people have to find solutions, and NoSQL was introduced. There are probably hundreds of NoSQL databases out there, each with slightly different properties. And you can try to map them in different way. I choose in this presentation to use 2 dimensions. The first dimension is the data modeling. The simplest data modeling that you can think of is key value. So databases like Redis allow you to do that. And of course, everything I say here is a great simplification because it doesn't have to be like a simple value. It can be a collection, it can be different data types, etc. So please forgive me for the simplification. The second, a little bit more complex data modeling is a document database when there is a key and the value is actually a structured document. You can think about it like a JSON structure or something like that. And you can actually update and read part of the document. You don't have to read all at once. A slightly more advanced or more complex data modeling is what is called wide column. And it's shared between databases like Scylla, Apache Cassandra, DynamoDB, and HBase. You can think about it as a key value, meaning that you have a partition key or a main key, then a sorting key, an ordering key, and then the value. And again, the value can be very complex. It's not really one value. In Scylla, for example, it's a list of columns. You can think about it as a table, each column with its own type, and you have user-defined types and additional complexity. And there are actually more and more type of more complex data modeling, from graph database to time series database, geospatial database, and more and more. So it's a very rich ecosystem of different NoSQL database, each excel on a different element. As I mentioned, Scylla excel in high availability, high throughput, and low latency. So it's a good fit mostly for online transactions. Another dimension to think about how to map NoSQL database is using the CAP theorem, which basically compare or put all the database on a map between availability and consistency. On this schema, Scylla is more on the availability side, and that's meant that, and I will demonstrate it soon, that even if parts of your cluster is down from some reason, the database is still available. And by available, I mean you can write to it and you can read from it. In Scylla have something called tunable consistency, which means that you can control the behavior of the database if a few of the nodes are done, and I will give examples soon. So this split between availability and consistency is useful, but it's a little bit naive. And the recent work presented more advanced modeling compared to the simple CAP. One of them called, I don't know if I can pronounce it, but it's PAC ELC, introduced by Martin Klapman, which actually compare not just availability and consistency, but also other properties like latency and consistency. And this makes a lot of sense to me, because if you think of a distributed database, imagine the case that there are no failure for a second. Okay, we're not looking for the failure use case, rather a normal use case, everything is running. Still, if you want to have high-level consistency, it makes sense that the nodes need to send more messages between each other, agree on some value. So the consistency costs usually the number of messages and complexity. And if you don't care so much about consistency, maybe you don't have to extend so many messages, and then you have lower latency and higher throughput. And the PAC ELC theorem or mapping take into account this property as well, and not just availability or consistency, which is pretty naive. Again, I apologize for the simplicity or simplistic view on the last 2 slides. So let me demonstrate what I mean in Scylla today with tunable and eventual consistency. So let's start with the most basic operation of a database. You write to the database and you read from the database. In this example, We have a small cluster of 5 nodes with replication factor of 3. That means that every data element is replicated 3 times. Now let's say that the client writes to the database. It chooses a random node in Scylla. In Scylla, all the nodes are symmetric. There is no like master or anything like that. Everything is symmetric. You can choose whatever node, send an operation there. And this node will be the coordinator for this specific request. In this case, replication factor of 3. So we will send the request to the 3 nodes that hold the data using something called a partition key. It's basically a hash across the entire cluster. In this case, you can see that 2 of the nodes respond with an ACK, and the last node, node X, didn't respond with an ACK. At this point, the coordinator actually cannot know if the writes to X succeed or not. It might be that the failure was before X persisted data or after. It doesn't matter. As long as the coordinator gets 2 response, since we are working with a consistency level of quorum, 2 out of 3 is a quorum, and an ACK can be sent to the client. Note that after this operation, although the client got a success ACK from the database, we don't really know if X is up to date or not. Of course, if we do the read with quorum consistency, the database will take the latest timestamp and return the right value, but there is inconsistency in the database. There are mechanisms to fix it later using repair another, but at some point, if someone asks only X, they might get an old value. Or if W and Z is down and someone asks X, it will get an old value, and this is why it's called eventual consistency. You can get, in a case of a failure, you can get an old value from time to time. The read operation actually works in a similar way. This time, the client chooses to use consistency level of 1 because he cares less maybe about consistency and more about low latency. So even if 2 of the nodes does not respond, it's enough for 1 of the nodes to respond and send a message back. So this work, I demonstrate how this works in one data center, but it's very similar in multiple data centers. Scylla often deploy across multi-regions. So you can have one region, for example, in AWS region, US East, one in Singapore or Frankfurt, and one in Africa. And as a client or an application, you can choose if you want to have a consistency level of global quorum, or more often you will use a local quorum. A local quorum means that the application only waits for an ACK from the closed data center, and the writes to the other data center are done offline, and the client doesn't have to wait for it. So it's very useful because the application gets a sub-millisecond response from the local data center, but of course, cross-region or cross-data center can take 100 milliseconds, and the client simply do not wait for it. So you have a case here of 3 data centers, all synchronized in an async way, and all application can read and write the data in a low latency. Of course, if a remote application try to read from here, it might not get the latest value in the first few milliseconds, and it will be updated after. Another important element of consistency is consistency of metadata. And that's actually, spoiler alert, that will be the part that Kostya are going to dive into in a minute. What is metadata? So far we talked about the data that the user insert and read from the database, but there is more to it. For example, with Scylla and other databases, we have a schema. You create a table, you change a table, and this schema need to be persistent as well. So this is what we call metadata. Another type of metadata is cluster topology. The database needs to know how many nodes are in the clusters. If you remove a cluster, add a cluster. So you have another layer of information that also need to be consistent. This data with current version of Scylla is propagated in the cluster using gossip protocol, which you're probably familiar with because it's very common on many different systems. Gossip protocol are very highly available, but they lack feature of consistency, and Kostya are going to talk more about it. Last slide for my section now. It's a proof in fire, if you will, of one of our customers. It's actually have a 3 data center deployment like I demonstrated earlier. And one of the data center, it's a public cloud vendor. It's not a private data center. It's a public cloud, and the site was completely burned down. As far as I know, no one was hurt, so no worry. But a lot of server actually catch fire, and you can see a screen capture from the Scylla monitoring here. And this dashboard, you can see there are 30 nodes in the cluster. 10 of them are unavailable and likely will never be available by the look of this fire, but the cluster continue to serve and continue to be available because, as I mentioned, Scylla is a highly available database, and we talked about it. I wouldn't share the customer name right now, but it's actually public information that he published himself. So if you want to, you can look it up. And by that, let me switch to Kostya to deep dive into the problem with metadata and eventual consistency. Kostya?
Thank you, Tsar, for this build-up for the problem description. In my part of the talk, I'm going to define in a bit more detail what problem we are solving, how we are solving it, and what benefits the solution provides to our clients, to our users. And I'll begin by just defining metadata, what is metadata, and why the current implementation of metadata consistency is not perfect. So the first thing we are actually moving to Raft is what's called database schema, and that's information about existing key spaces, indexes, views, and access rights. And but also the schema defines the power is defined by the power of data definition verb, like what you can do to change schema. So in, say, relational database, you can even change the type of a column, and the data is going to be rebuilt for you on the fly, so that and if there is a consistency violation, and that's the whole operation is going to be rolled back. So the schema includes basically what objects you have in the database and the verbs you can that you have at your disposal to operate on these objects. And in Scylla, because of the approach that putting the high availability first, replicating schema statements is a known implementation. It's not the same path. It uses its own right path as than replicating data. The schema has to be present on every node. Every node has to know the format of every table, the replication factor, and such and such. So the way it's being replicated is that it's allowed to change schema on any node, and that node is then responsible for pushing that information to every other node. So, but because of the high availability requirements, strictly speaking, you can, run the schema changes in isolation. You can have a single node in the cluster, and that's and use that node to create a new table, and then expect that it's eventually propagating to all of the other nodes in the cluster. This naturally brings the problem that data can have slightly different schema, and Scylla can live with that. Scylla clients can live with that. There is an on-the-fly conversion between data formats, and Scylla doesn't allow verbs that change schema that would sort of lead to an incompatible change in the data format. So you can add columns, you can remove columns, and this is going to be just hidden for you on the fly. When you request a newer version from an older client, like an added column is going to be hidden from the result. When you add a new row from an old client, there's going to be default value substituted for the column that the client is not aware of, and so on. So this is, of course, like if you think about it from like the quorum point of view, for your rights, you know there is this rule of eventual consistency that your read and write quorum should be larger than the total number of your nodes. So like if you have 3 nodes, you should write with quorum 2, and then you can read with also read with quorum, or you can write with quorum all, and you can read with 1, and that provides consistency. But when you think about schema, it's not the case. You can create a schema on one node and then a different version of it, like table on another node. And in this example, in this illustration, I'm showing that it's eventually reconciliated. So eventually the schema, the mutations that you perform on this disjoint parts of the cluster, they converge. But it's not always possible. Like schema changes can also fail in some ways and in many ways, or the operations, even though there is a really limited set of operations you can do, still it can lead to an inconsistent state. So if you, for example, if you create a table with one definition, and you create the same table with the same name but a different definition on another node a bit later, then that later definition is going to win, and the old definition is going to be shadowed, and all of the data that you put into that old table is going to essentially disappear because the data is not brought to the new definition. It's just the definitions that is being replaced. So this is not always nice. Plus, as I said, you might want to have more powerful verbs that just are, cannot work in this CRDT manner, that do not converge naturally. And this is why, if you think also about it from quorum perspective, like it is natural to expect a quorum of nodes for schema, just like you expect a quorum of nodes for your data. And the quorum of nodes for schema would be half of the nodes plus one. So the same problem is present for eventually consistent topology changes, even though Scylla does require like all of the nodes to be up, or at least recommends all of the nodes to be up for topology change operations. And let's just talk a bit about what it is. But still, because of the same underlying mechanism, the same inconsistency might happen when you perform topology changes. So let me give you an example. Topology is like is the set of nodes in the cluster is set of data centers, like this. The what's often called failure domains, what data centers, what racks, what servers you have, and it's the ownership of the mapping of the data to the node. So like what node in the cluster owns what partition or part of the data. So Scylla uses consistent hashing. It's a very widespread way of mapping very large collections to a distributed set of nodes. The goal of consistent hashing is to minimize data movements when you add and remove nodes. And the way it achieves that goal is that it hashes every key and throws that hash on this conceptual ring that's called the token ring. And so that hash of the key is called the token. And the entire space of that conceptual ring is being split between the nodes that are present in the cluster. So the nodes are also hashed. The hash values are also thrown at the ring, and the range between that node's hash and the previous node's hash belongs to that node. So it becomes the so-called primary range of that node. And every node or in the cluster is a primary for some range, and can also be a replica or called a secondary or tertiary replica for some other range in the cluster, depending on your replication factor. And so the token partition is like these three things. It's like the hashing, the ring, plus plus the information on the replication factor. So, and when you bootstrap the cluster like that, every node decides on a set of tokens that it will own. These are random values. They are advertised to the ring through gossip. So eventually, all of the nodes learn about them. That's why we have in Scylla this ring delay parameter that is a sleep time between starting a node and actually proceeding with boot, proceeding with streaming, that is used to let the tokens propagate through the ring, propagate through all of the other nodes in the cluster. So as I said, token metadata is very much connected to schema, because they together define mapping between data and the nodes. Because you need to take into account not only the tokens that say a node can generate and advertise, but also the definition of key spaces and the replication factor to properly learn to know how to perform the right queries, and how to achieve the right quorum for your operations. So just like with Schema, Scylla stores this information persistently on every node. So every node is allowed to have a slightly different version of that information, since it propagates eventually. And this, of course, can lead to issues. One example is, like, let me give you an example of a scenario. So suppose you have a cluster of 3 nodes, and initially all of them are up. They advertise their tokens correctly, and every node knows about every other token. Every node is responsible for advertising its tokens through gossip. Then the cluster goes down, so all of the nodes are down, and then only 2 nodes are up, and the node C, it just remains down. So A and B, they know that C exists, but C does not advertise its tokens. So whoever is, like, if you try to add a new node to that to that ring, the local view. So the local view of nodes A and B is going to contain the information about the tokens of C. But if you that new node that just came to the ring, it's only going to learn the information about tokens of A and B. So that's an example how, because of eventual consistency algorithm for propagation of token metadata, you can have incomplete information on the node, and that leads in turn to wrong write concerns, wrong replication factor for your writes. And of course, Scylla, like, this is not good, and Scylla can sort of, this is an operation Scylla can and has tools to recover from. And even though, even moreover, in the documentation for Scylla says that you just shouldn't do that. You shouldn't do topology changes if you have down nodes. Plus, you can use repair to repair your cluster, and you are supposed to run repair before every topology change according to the manual. But still, this is not the perfect solution, and since you can get into this situation, and you can, like, it's all the the responsibility is on the user to do the repairs, to check that the cluster is alive, to not make mistakes and not perform topology changes when any of these predicates is false. So, and we would like to move to more of an automated implementation. uh, that's the primary reason for having a different algorithm running that. So so just like with schema changes, we would like to have consistency under all circumstances. And we would like to make the topology changes much quicker, so that we don't rely on gossip, which is naturally slow. You have to wait until all of the nodes learn about the changes, since nodes speak to each other. They don't speak to the originator of the change. It's not pushing these changes. And finally, a few words about data. Having strong consistency for topology and schema changes is a prerequisite for strongly consistent features like lightweight transactions. Even though we do support them, but you can get into a situation with topology changes when you violate consistency of lightweight transactions. This is a well-known fact. And moreover, like with strongly consistent tables, which we call tablets, and this is one of our goals as well. So to sum up, we have 3 strong needs for strong consistency, and we decided to use Raft for all of this, and Raft is implemented in 5.0, and in that part of my presentation, I'm going to talk what we did with Raft, how we use it, and how it solves the problem. So Raft is called a protocol for state machine replication. The idea of that, like, imagine you want to have a reliable implementation of some process, and you want to put it to make it reliable. You put it into a collection of servers, so that if any server fails, you have other servers that would replicate what that other server, that failed server, does, and that would provide that kind of reliability. Then your goal is to make sure that every server does sort of contain the same state, contains the same data, and performs the same operations on the data. The idea that Raft exploits is that if you have a persistent log for all of the changes that every server performs, and you append entries to that log in the same order on every server, that can guarantee the transitions between the states, so that these transitions will be also done in the same order. Essentially, every agent in this sort of setup is first persistent the changes in its log locally, and then applying at some point the sort of committed changes to the uh, to the um, to the local state machine. In terms of Scylla, that kind of replicated state is schema and topology information, and the log that we use is just the local tables on every node that would store the topology and schema information before this information is being applied. Okay, and there are some questions on the chat, so I will just take them on the stride. And the first question is, how many nodes can be added in a Scylla cluster, and is there any limit on the nodes? So there is no limit that I'm aware of. There is so you can have a very large clusters, but typically you don't have that, like, actually that big clusters, because Scylla scales well vertically, so it can use quite beefy Amazon EC2 machines, 64 cores, 128 cores. It scales well to this, and on this, and so the other reason is that, like, you can have a lot of storage on these machines. So typically you have like 3 to 10 machines in a Scylla cluster, but later in this presentation I'm going to talk about scaling Raft to very large clusters as well, so stay tuned. The other question is, what type of replication can we configure? Streaming replication, logical replication, all nodes are in a read-write mode, or do we have a setup in like a master slave? So in Scylla, all of the nodes are read-write, and all of the nodes are primaries for some ranges and secondaries for some other ranges. In fact, we have what's called a vnode setup. So every node is responsible for virtual buckets or virtual ranges. So it's many ranges per node, and that also makes the topology change more smooth. So the replication algorithm is neither streaming nor logical. It's so if you look at all of the databases, including Raft, you can split them like into very broad categories. First is a database that first performs some operation, and then it replicates that operation, and that's like say MySQL, Postgres, and they replicate from the write-ahead log or from a replication log after the operation is performed locally. The second category, and that includes Scylla, and that also includes Raft based databases, is when you first replicate and then you perform. So the difference between the current implementation, how Scylla performs and replicates, and Raft, is that currently Scylla replicates optimistically to every node and performs optimistically on every node in a single hop. So you push data from the client to the server, it gets to the coordinator node, and then it's being pushed to all of the replicas from that coordinator node. And that coordinator node, if you have a token-aware driver, what we call a token-aware driver, is most frequently replicate itself. So it's being just replicated to very few nodes. And in Raft, it's very much the same, but it's not actually committed at the point when it's replicated. It's first pushed to the nodes, and only when we get the quorum, when we get the majority, we tell all of these nodes, hey, now it's okay to apply that data. Now it's okay to execute that query, and so on. So that's the kind of replication we use. And what we actually replicate is also a good question. So like you mentioned, logical replication, streaming. Scylla replicates things that are called mutations. So these are writes against partitions or individual keys. And these writes, the good properties about these writes, why we call them with the special term mutations, they are idempotent. So every write is assigned with a timestamp, and it's safe to apply that write over and over again. This is what Scylla uses for repairs. It's just if it's safe to reapply rights, which Scylla is Scylla considers that they are not present on that node. So that takes them from some other nodes and reapplies them, and can do it many times. Another question, what's the minimum requirement in terms of RAM CPU for testing purposes? Well, I am going to take that in the end, so let's move forward. So let's go back to Raft. I mentioned already, like they spoiled already what I'm going to talk about in these slides. Raft consists of like three major things. First is that state machine, what we want to replicate. In our case, that state machine contains topology and schema information. The idea of the state machine is that it's some program. In like it executes, a state machine executes a program, transitions from state to state. We want to do it predictably, and we want to have an identical copy of the state machine, identical copy of the schema on every node. The second part of Raft is this write-ahead log that every node has. And Raft uses a leader to decide on the order of the write-ahead log. At any point in time, there is this active leader that's only one node in this very large, potentially very large cluster, that's appending entries to its log and replicating that entries to other replicas and making sure that they have them in the same order. When the majority of the nodes in the cluster get them in the same order, the entries are applied and to the state machine. So the state machine just gets the create key space statement or add a node statement and so on. So, and there is this third part that's managing this whole thing, and that's called the consensus module. And part of its work, like I said, is first tracking which replica has which size of the log and state of the log, and which entries can be applied, and which entries need to be replicated. But also, it's responsible for things called leader changes and configuration changes, that is, conditions when the leader is down. So when you like apply this to Scylla, the big advantage of using Raft instead of Gossip is that you immediately switch to this push-based paradigm. So as soon as you do any change, you forward it to the leader, it gets to the leader. The leader is responsible then for pushing it to all of the followers. And it happens immediately. The leader is acting like it's proactively pushing the changes, not waiting for the followers to contact the leader. It's constantly pushing the changes until it gets them propagated to the followers. But also it creates sort of a new problem because, like I said, the whole operation of Raft is decomposed into like normal operation when there is this beautiful leader that decides on the order and pushing the information to replicas, and when you have to elect a leader. And before we talk about leader election, let's talk about how we actually understand that the leader is gone, how we decide that we need to elect one. So the vanilla Raft answer to that is that the leader, well, first of all, most of the time, it's actually doing some useful work. It's pushing information to followers, so they are aware that the leader is alive. If you have a busy cluster, there is always some traffic coming from the leader to the followers. But if you have an idle cluster, which is very frequent with schema changes, you don't run the schema changes that often. The leader in vanilla Raft is responsible for pinging the followers, for sending these empty packets to the followers saying, hey, I'm alive. You don't need to run the elections. Things are fine. And followers, in turn, they sort of track the last ping time. If they haven't been pinged for a lot of time, for like 10 intervals, that's called an election timeout. They decide and they try to nominate themselves and become a leader themselves, and so that we preserve liveness in that cluster is not stuck. So when the election happens, you have a node that says, hey, this is an election timeout. I haven't heard from a leader. I want to become a leader myself. That node, in this case, S1, in this example, it transitions to this special state in Raft that's called the candidate state. And it tries to collect the votes from all other members of the cluster. And in this illustration, you can see that our S1 eventually does become a leader, And most of the nodes, the required number of nodes, that's the majority, like in this 5-node cluster, 3 nodes, including S1, got to vote for S1, so it needs to collect 2 votes. But the problem is that, as you can see, by the time that S1 becomes a leader, like S2 and S3, they also become candidates and try to run an election. So in vanilla Raft, there is this potential race, and that's actually has been recognized as a significant issue with this just straightforward any straightforward implementation, that between nodes trying to become candidates, trying to win elections, and those stealing the votes from each other. So imagine you have a 5-node clusters. 2 nodes try to become leader. Neither of them can. It is possible that neither of them, or like 3 nodes, no node can get the majority of the votes. You, this situation is called the split vote, and you have to retry, and you retry after some election timeout, and that sort of prolongs the interval during which the cluster is not available. So in order to solve that problem, Vanilla Raft offers this thing is called the randomized election timeout. And what it does is, like, there is the selection timeout when, like, say 10 ticks, when every node is eligible for becoming a candidate, but the node doesn't immediately become a candidate, to not create a thundering herd problem. It waits for some randomized timeout. Also, that's already, we call it election threshold, and sometime in this random range, it will become a candidate. That typically helps to win the election. But however, if you get more nodes, the race situation becomes more likely. And when we implemented Raft, we ran some experiments, and we discovered that as you get to like 100 nodes, 200 nodes, it's very likely that you have prolonged intervals of unavailability. With 300 or 400 nodes, it's pretty much you never get to a situation when a leader election succeeds. So we spent some time looking at this issue, including we tried different approaches, and one of them was to use Gaussian distribution of the timeout. Unfortunately, it does help. It does help for medium-sized clusters, but it still suffers from the same issue. Like, as you get more nodes, you pack that interval that between election timeout and election threshold, and you have split votes. And if you obviously just increase the election threshold, and you randomize the data even more, so you get you increase unavailability of the cluster. So the solution that we in the end arrived to is that we chose our election threshold to be proportional to the size of the cluster. It was a great advantage. We now can our tests show that even very large cluster, like 10,000 node cluster, 10,000 node clusters, they can quickly elect a leader and move on even in unstable networks. Another thing with vanilla Raft is this ping, like I mentioned, this ping interval and ping time. If you remember, Scylla uses a lot of partitions and a lot of tokens to manage the data. So every node is responsible for many tokens, and we plan to actually use Raft for every token eventually. That means that since every token thrown on the ring that a node owns has its own replication strategy, replication topology, it means that we are going to end up with a lot of groups. What we call a group is a single instance of Raft protocol. That would include all of the replicas for this token. And if you remember, I began by saying that we want to use Raft for schema and topology and for data as well. So at some point, we would get into a problem when we have the number of pings in the cluster happening in like in every second, proportional to the number of groups in the cluster. So in Scylla, we share the failure detector between all of the groups, and we moved it out of the cluster so that it's a separate external entity, external module that all of the groups share. And that allowed us to reduce the number of pings. We just the number of pings every node performs is proportional to the size of the cluster, not to the number of the groups. That's much better. But that created a new problem, in if you say depose a leader in the cluster or remove the leader from the cluster, it stops pinging the followers. So that's how followers naturally detect that the leader is dead. If you have a shared failure detector, you can remove the old leader, say A, but B, C, D, and E might think that it's still alive because it's still present in some other group. And so we actually found it in tests, and we implemented a special solution for that case when if a leader is removed from the cluster, but some nodes still believe that it's still a leader, they can, in certain circumstances, search for a leader. So they believe that the leader is alive. They try to forward the information to it for execution, but the leader does not respond. In this case, nodes, they send a broadcast message to all other members of the cluster saying, hey, how about telling me if you heard from the leader recently, if you got any entries from that leader. And if there is no response to that, nodes become candidates and start an election. So I just mentioned that, and I'm running out of time. I just mentioned that I want to leave some space for questions, so I will skip over some slides. That in Raft, one of the major reasons that why actually we chose Raft was that the configuration of the cluster, what nodes are present in the cluster, is also part of the protocol. And the way it's done, so Raft actually allows you to change the size of your quorum dynamically. You can add a node or remove a node to your cluster as part of normal Raft operation. This information is being committed to Raft log. This is how every node gets that information, and because it goes through the same log, it's linearized with, not linearized, but it's in the same order as all of the other operations in Raft. So you can easily make sure and prove that no record is lost because you say you remove more and more nodes, and you wish to, like, multiple nodes from the cluster, you add multiple nodes or you replace nodes and so on. And in Scylla, we use a joint system for configuration changes. This is a more advanced way of changing configuration. That's you can think about this as as a kind of a two-phase commit. When every configuration change first is added as initial stage, and it instructs every node to commit every record in this joint configuration, that includes the old and the new quorum. And later on, when this joint configuration propagates to the majority of both old and the new quorums, the second record is committed that actually completes the transition. And these kind of changes are much safer. And I'm going to talk about it in a minute. Another matter that is worth mentioning about Scylla Raft is that we were aware of 2020 Cloudflare outage. That was Cloudflare was based on etcd version that didn't support a major feature of Raft. That's called what was called pre-voting. And later versions of etcd have it on by default. So our implementation also has it on, and the basic idea of this is that it introduces a special state, an intermediate state for every candidate when it doesn't actually start an election, but only checks if it can become a leader. And that allows to run sort of dry run the election without disturbing the cluster. A very important property when the cause of the outage in 2020 with Cloudflare was that there was this disruptive leader which would believe that it needs to elect themselves again and again. That would disrupt existing leaders in the cluster. They would step down, and that would continue on and on. So with pre-voting, that's not possible. All of this combined allowed us to actually simplify some parts of the Raft. So both pre-voting and joint configuration changes, they are optional in vanilla Raft, and they are not optional, they're mandatory, and there is actually the only way we do it in Scylla implementation. So that allowed us to remove some parts of the implementation, making the protocol simpler and more reliable. So to summarize, we at Scylla went to great lengths to just to make sure that our Raft implementation supports our scenarios. We wanted it to be available for schema and topology changes. We wanted topology and schema changes to be quick. We wanted it to scale to the large number of nodes and the large number of groups so that every token can have its own Raft group. And we adjusted the Raft implementation to serve our needs, to just do what we need. Finally, having explained what Raft is, let me just briefly cover what are schema changes and how we run them on Raft. It's, well, you could say it's a breeze. Raft, but you have to keep in mind that Raft itself doesn't provide a mechanism for like this exactly once execution. It doesn't provide a mechanism for getting the latest schema from every node. When you say a client sends a create table to some node, Raft does not guarantee that that node has the most recent version of the Raft log and the most applied version of the Raft log. So we implemented another algorithm on top of that that provides this exactly once implementation, or what would be more correct to say at most once implementation, when it uses a special marker, a schema version marker that is that signs every schema change, so that a schema change that has already been performed is not like it's safe to execute it again. So it's important, and we can easily retry some schema changes for which we don't know if they succeeded or not, for which we like there was a leader change or a node down during the schema change. And this all works under the hood. So the client simply gets a success, a valid error, like there is already such a table with the same name, or the table doesn't exist, or a timeout. So that's worst case, the client can get a timeout because like the majority of the nodes in the cluster are down. So having said that, and having said that Raft requires a majority of the nodes to be live to perform schema changes, how did we actually define that new balance between availability, like the total availability of Scylla clusters, and requirement for majority for that is set by Raft? And here, let's remember, let's go back to this idea of different versions of schemas allowed at different nodes, and schemas being transferred between nodes through this eventually consistent protocol that could be, that just allows one node to fetch the latest schema from the other node. So we preserve that part. We allow the clients to send the writes with some older schema versions, and we allow the nodes which don't have the right schema version. So if the client just sends an information with the most recent schema version, but that node specifically haven't heard from the leader yet. So that node would just get to the neighboring node and find that schema there, and we'll try to get that schema from that neighboring node. And here you can see that we have node S1, S2, and S3, and every node here might have a slightly different version of the schema at every particular instant. But you can see that the transitions, what we actually changed, you can see with the colors on that illustration. So it's not that some nodes are already yellow and some nodes are still green. That's impossible. So all of the nodes transition from one state, from one version to another version in the same order, green, red, yellow, green, red, yellow, and so on. So even though that might happen in slightly different instance, it's always the same order. And finally, I've already mentioned that we've switched into this push scheme. We sped up greatly our cluster assembly. Now our cluster assembles in like under a second, less than a second. And in our test today, we set ring delay to 0, skip wait for gossip to settle to 0, and it all works. To summarize, concurrent DDL is now safe. Anomalies such as spurious errors, shadowed key spaces, or columns are impossible. Schema propagation is much faster. Topology changes propagation is much faster and more reliable. And starting from the next major release, Raft-based schema management will become the default. There is also a problem that we introduced. Not all changed, not all changes like always come with no price. And the particular case I'm going to talk about is a 2DC case, is like what we call a 2DC problem or split brain problem. And if previously some users would expect, like were used to having one DC continue running unaffected if another DC and 2DC setup is down, is permanently down, this is no longer possible. So we already have a patch that allows you to redefine the quorum in these circumstances, to reassemble your cluster and run in a single DC if your other DC is down. But we generally recommend with switching to Raft, switching to the stronger consistency, to have an odd number of data centers, odd number of nodes in the cluster, so this problem doesn't happen. And I would be curious to know if this has any impact on you. So with that, let me switch back to Tzach. I had a lot of slides today, and I wanted to introduce some extra slides. So thank you for your patience, and there were also some questions. So I think it wasn't all wrong. So
Thanks, Kostya. Just to recap the current status of the Raft implementation. The Raft implementation is included in Scylla 5.0. You can, right now or after this session, download a Docker instance, for example, of Scylla 5.0 release candidate, enable Raft and actually use it. But that's only our first step in the Raft journey. And our plan is to build many more features on top of Raft. So schema consistency is the first, topology consistency is the second, and later we plan to use data consistency on top of Raft as well. So a lot of good stuff are coming. And with that, let's open the floor for questions. So the first question is for you, Kostya. I know that Scylla already used another consensus algorithm for lightweight transaction, which is based on Paxos. And my question, why didn't you reuse Paxos for other purposes? Why you decided to move away from it? And do you plan to, now that you chose Raft, do you plan to go back and remove Paxos from lightweight transaction?
yeah, so let me start from the second part. We are not planning to remove Paxos from lightweight transactions. So lightweight transactions as a feature is highly defined by Paxos. It's like properties, its semantics is defined by Paxos. And what I mean is that it is alive, it is available, even even if some partitions are, if some members of the cluster are permanently down, so it is still going to proceed on those partitions that are alive. It doesn't require a chosen leader, yet we don't want to use it for our topology and schema changes. And the main reason is that Raft includes configuration changes in its core. So we have a very neat algorithm for adding and removing nodes, including adding and removing multiple nodes to the cluster, which would be difficult to add on top of multi-Paxos that we use for LWT. So, and going forward, if you like, generally, Scylla is a multimodal database. I like it personally as an engineer, and I think that's the strength of it. So having some like, so there is this big debate in the community of whether to use leader or leaderless protocols for consistency. And I think having both is just like you get, especially if you don't inherit the deficiencies of the two, like because they are completely orthogonal. Like we use, it's not like you have both on the same. You define when you use what. It's a good thing.
Okay, thanks. Another question that we got is on Scylla and Kubernetes, which is becoming a popular deployment option these days. So what is recommended PV? I guess it's persistent volume. So the answer is first, it's not related exactly to the topic of this session, because the Kubernetes is just an underline, like a cloud or whatever deployment. But just to give a quick answer, we always recommend to use SSDs and Ferial or local disk for Scylla, because that they have the best performance. And usually when you use Scylla, you're looking for good performance. You can use Scylla with slower disks, but then you lose some of the benefits. So I'm pasting a link here to Scylla operator and Scylla Kubernetes documentation. You can continue exploration this alternative there. Okay, I don't see more questions. So thanks everyone. Just before you leave, I will ask you to complete the last poll that we created on your current deployment, maybe with the traditional relational database that you have right now. We'll appreciate your inputs. We are using it later to understand your journey. And by that, we conclude the session for today. Thank you very much. It was a pleasure.
Thank you.
And thank Kostya. You did a lot of work today. It's much appreciated. And you can jump on our Slack and continue the discussion there. We'll try to answer more of your question over Slack. So
yeah,
thank
just
you
tag
very
my
much.
name. I'm Kostya on the community Slacks. If you have more questions, you're welcome to ask them.
Thank you, everyone, and have a good night.